There we go. So it takes about 5-10 seconds to get that part started. All right. So what we'll do today, the first thing I want to do is to illustrate that you can actually test this program in online GDB, or if you have code blocks installed, or if you just really prefer the command line way of doing GDB, they're all doable. Okay, so I do want to illustrate that because I think it's really kind of important to be able to run this code in um, online GDB or some kind of debugging environment and get to understand what we are dealing with here. So we have that PTR2, and your program has to reflect the C code. In other words, I'm not really looking at I'm not just looking at the final result of whether the swap happens or not. I'm looking at whether your program, implements the swap subroutine correctly or not. So, so there are ways to quote unquote hack this program so that it works. It seems to work. Those methods are not going to get, points because that kind of defeats the whole purpose of having this homework assignment. It's kind of like okay, this is something that I saw, but I think it's very analogous to people who try to shortcut this. There was one time I took my kids to their swim lesson, and I saw this mom sitting next to me, and she tied her Fitbit to her dog, and then she instructed her dog to basically run around. It's kind of like that. Okay, it defeats the whole purpose of having a Fitbit, okay, which is to motivate the person, not the pet, to run around. So I should have said the parent. I shouldn't use the gender because that seems to imply something is gender specific, but that was not my intention. All right, um, so this is the program, right? I mean, I can remember this program by heart because that's a very typical way to swap the content of two different locations. So it's not the code itself is not difficult. It is the implementation that can be a little bit tricky. So in main, we have two variables, which I think I cannot remember, I think it's x and y. So uint underscore t, x and y. And you can do whatever you want with this C program. You can initialize x and y with whatever value you want to use, and then you call the subroutine swap, and we have to pass the address of x to one, and then pass the address of y to the other one, and then we get rid of printf. There's no need for the printf here. I mean, you can keep it; it doesn't hurt, but it doesn't. I mean, it doesn't really need to be here either. All right, so this is the code, and I think once I select the right programming language, it should compile and it should run. So I go to debug. All right, so even with a simple program like this, I can show you a few things that are kind of useful when you are using GDB, and I really think GDB or any debugger, okay, if you want to use VS Code, that's fine. Okay, I'm pretty sure it has equivalent capabilities. So we're going to put a breakpoint in swap. So if I put a breakpoint at the label swap, it is at the entry point of the subroutine. So now we can run the program. So R just runs the program. So at this point, there are a few things we want to investigate. Okay, what exactly is PTR1? So this is what PTR1 is. It is an address that ends with B, B-E-E, and then PTR2 is another address that ends with BEF. Okay, so we want to know, okay, but are those actually the addresses of X and Y in main? So in GDB, there's a command called Backtrace, or in short, you can just type BT. So what BT does is it shows you all the call frames that are active at this point, okay, at the breakpoint at this point. So we can see that main calls swap, and that's exactly where we are, which is in swap, which is in main.c on line 15. So what you can do now is to look at the pound. These are the frame numbers. So now you can say frame 1. What that does is, without changing the execution point, it doesn't really move the execution point, which is still on line 15 right now. It doesn't change that, but it does change the context. So right now we are no longer in the call frame of swap. We are now in the call frame of main. And as a result, we can now look at x and y. So we can say print x. X has a value of 16. We can say print y. Y has a value of 3, which is kind of what we expected because of line 24 and line 25. But more importantly, we want to print the address of x. So when we print the address of x, you can see how this is an address, 7FFF, a whole bunch of stuff, and it ends with EBEE. Okay, so that is what we want to see, is we are indeed passing the address of a local variable of main as a parameter to swap. All right, so if you want to switch back to the original frame, which is swap, you just have to say frame 0. So frame 0 always refers to the current or the most recent frame, like so. So now, we have another question. Okay, PTR1 is a parameter, and as a parameter, its value is the address of something. So now the question is, do you think PTR1 has its own address? Well, the answer is yes. Okay, it has its own address. So when you say print, ampersand PTR1, you can see how PTR1 has its own address. And you can also see how the address of x, it ends with BEE, and you can see how the address of PTR1 ends with BB8. Now they're not exactly very close. That's because we're using the 64-bit version of the compiler. So addresses, they're all 64-bit wide, and that's why they're kind of big. But it is lower. Okay, it's the relative position that is important. You can see how the address of PTR1, which is the address of the parameter, is lower than the address of local variables in main. So that part is kind of important. Now I get to catch up with the text channel a little bit. All right. Yes, Nathan is correct. The lab on this Tuesday is due next Tuesday, same time. What's the value beside 16 and 3? All right, so in single quotes, those are the ASCII code interpretation of 16 and 3, because 16, as a 8-bit unsigned integer, most of the time people want to see it as a char, and that's why GDB is trying to be a smart ass and say, hey, if I think you want to see this as a char, and let me tell you what it is representing as a char. That's basically what it is. But in this program, we don't really care. We really just want to look at these as 8-bit unsigned integers and not so much as chars. There we go. No, the addresses obviously will not be the same as in TTP-ASM, because the code that is running in online GDB, this is probably coming from a virtual machine, that has a 64-bit address space, which is like gigantic. Okay, the TTP, the text-to processor, only has an address space of 256 bytes. So no, the addresses won't even be close to what you'll be seeing. However, understanding the concepts, you should know how the stack should be utilized when the equivalent code is running in TTP. So that is an exercise that you should do first, is to basically, without thinking in assembly language, just looking at the C code, but thinking about how the stack should be utilized, you should be able to figure out the position or the locations of the local variables. These two are given in the code that I gave you, in as a part of the lab. So that portion is kind of spelled out. But the other portion, which is in the swap subroutine, that portion you should be able to figure out, even without knowing the assembly code, just by understanding what a frame is and how things are passed on the stack. You should be able to figure out the locations of where you can expect PTR1, PTR2, and the local variable t to be located. The extra lab today that I just made, just for you guys, for this semester, should also help to clarify, those concepts. So hopefully, everything will kind of tie in. They will just kind of, hopefully, they will all click. All right. Yep. So Chris is correct. TTP only has 8-bit as its memory space. It is extremely modest because the idea is we just need a very small, tiny little architecture to illustrate the concepts. But the concepts, once we understand, they apply to just about any architecture out there because they are fairly standardized concepts. Cool. All right. And somebody asked whether the TCP has any type of printf-ish kind of output, and the answer is okay. The official answer is no. But if you want to pretend and kind of go through a lot of trouble to emulate, standard out, there's a way to do it. It's super ugly. I can sort of show how it is done, but I think most people would just not bother to do it. So I'm not going to show it unless there are people requesting it, or I can do it, during the lab time today, just so that someone can see it. Alrighty. So I'm not going to finish this code. I want you guys to do it. Okay? The code in this program, really is simple. I don't think I need to share this code with you because you can probably just retype it or just copy and paste from the lab without using a lot of time. But the key is to understand the concepts first. Okay? Understand the concept in C/C++ before you even attempt to write the code in assembly. So that is the important part. All right, cool. So I did promise that I will show you another sample program, not the same one as on Tuesday, so that you can kind of look at a different program and kind of potentially gain a better understanding of how subroutines work. Now, when I say how subroutines work, you guys will say, but Tech, you're being very specific. This is how subroutines work in using TTP, using text toy processor. Well, yes and no. Okay, there are certain aspects like the mnemonic and also the opcode. Those are all very specific to TTP, but the approach is not. Okay, the approach is actually fairly universal. So if you look at how a compiler generates code for the AVR platform, okay, that's used as the Arduino controller board, it's about the same. If you look at the compiler, how the compiler generates code for the ARM architecture, typically used on mobile devices and also the Raspberry Pi, is about the same. Okay, those opcodes are longer, more complicated, and potentially can do more things at the same time, but it's not much different compared to what we are dealing with here. All right. So I'm going to show you guys a different program now. Okay, so we'll go ahead and change this program out a little bit. Okay, and this time I'm going to show you something that uses a string. Okay, so I'm going to use a string here. So const char star, we'll call it str, and we'll make this just A, B, C, D, E, F. Okay, so it's not a fancy string, just a little string here. And we're going to make a subroutine to process this string, and we'll try to figure out what it is doing and how it gets it done, and more importantly, how do we translate that into assembly code. So this is our mystery function. We'll just call the mystery function F1. So what F1 does is it will take const char star ptr, so it takes one argument as the pointer, and in the function I'm going to use my favorite. Okay, it has one single return statement, and you guys go like, no, not the ternary expression again. Yes, ternary expression. Because it really is quite useful. It really is quite useful. So the condition we are checking is really just asterisk PTR. In other words, I just want to see whether PTR is pointing to a null character or not. Okay, if it's not pointing to a null character, star PTR is going to be considered true. If it is pointing at a null character, then star PTR is considered false. Okay, so if it is true, I'm going to say, let's go ahead and return this value, which is 1 plus f1, and I'm going to pass ptr plus 1 as my parameter to the recursive call. Colon, okay, which means now we specify the false value. What if star ptr is false? Which basically means, this is a null character. Then I say, let's return 0 in that case. Okay, so this is a mystery function, and we'll first try to figure out what this mystery function does, and then we'll figure out how to implement the mystery function in assembly language. Okay, so over here, yep, Chris is right. This is just the recursive version of string length. It's not very exciting, is it? But that's okay. We're gonna, try this out and see whether that's exactly what it does or not, right? So to test whether this works or not in a regular, C-type environment, I don't have a choice but to specify a variable so we can actually store the return value. And the reason why we have to do this is because even though I can, but it's not really that easy to put a breakpoint in at a place where the return value is stored in what is equivalent to our register A in the 64-bit architecture of x86. And on top of that, the compiler can be a smart ass and optimize that code out completely. That can happen too. So I'm just going to have to make sure that we have the function call, and it does come back to store the return value into X. Just to make sure that the compiler doesn't optimize something out, and so we cannot get to see the result of the program. Alright, so this is the code, and if I feel confident enough, I can put a breakpoint here. I'm checking the things that I typically, where I typically make a mistake. I typically make a mistake of forgetting to do a +1 over here. Then it becomes an infinite recursion, right? Because we are not moving on to the next char, so we will never get to the Null Terminator if I don't advance the pointer. Okay, I just heard something. Probably someone is trying to get into Google Meet from outside of the Los Rios network. That's why it makes that announcement, because otherwise it's automatic. People can just join without having me to admit people. No, it just started a new window, and I'm not seeing the request to join. Not sure whether someone is trying to join or not. Well, I guess if that person is trying to join, I'm gonna put it in the text channel. Okay, try to join again. Alright, so obviously it doesn't apply to those of you who are already watching this and listening to me, so this only applies to the person who's trying to join a moment ago. Alright. Oh, okay. It's Mr. E. Mr. Wilson E. We know the name now. We know where he works too. Yep, we did a little bit of detective work and found that out. It's kind of interesting. Alright, so we're going to debug this program. Okay, click debug. And now we run the program. Just type R to run the program. And now we are on line 24, which means X should have a value already. So we say print X. and x is indeed 6. Okay, so that's pretty right. That's pretty cool, right? Because this is a recursive function and it works. Okay, it just basically counts the number of characters in a null terminated typical null terminated C string. All right. So let me see if there are any questions about this code at this point. About the C code, so don't worry about the translation into TTP ASM. So right now we just want to understand how the C code works. So we got a few people typing away, so that's good. That means people are paying attention and not just go like, yeah, yeah, C code, I get it. Very good question, Davish. The answer is yes. So every single invocation makes a new frame. Now, if you're still kind of questioning what is a frame, because we did talk about frame already in a previous lab, but the lab tonight, hopefully will also help to clarify what a frame is. So a frame is basically a contiguous area on the stack where it contains all the local variables and all the parameters, as well as the return address specific to an invocation of a subroutine. So when we think about subroutines, there are two aspects of a subroutine. When you look at line 12 all the way to line 15, that is the definition of subroutine F1, and there's only one definition of the subroutine here. But when you look at the invocation of the subroutine, then it really is dynamic. It's a runtime kind of thing, because at the beginning, right before the call to F1, we have zero invocation of F1. There are no frames corresponding to F1 at that point on the stack. But as we call F1, from main, then we have one frame, and then within F1 we call F1 again, then we have two frames. And when that invocation calls F1 again, then we have 3 frames and so on. So we have 1 frame per invocation of the subroutine. So it's really important to understand the differences between the definition of a subroutine, which is really static, versus an invocation of a subroutine, which is a runtime kind of concept, not a compile time concept. Yes, so each frame has its own parameter, has its own local variables, and its own return address. Those are all independent. So all the frames are independent to each other, unless you do something to kind of make it not independent. Okay, what is 1 in front of F1 in return? It's exactly what it is. It's 1 plus. Okay, we take the return value of recursively invoking F1, and then we add 1 to that, and that becomes the return value when PTR is pointing to something that is not null. I mean literally, this is just 1 plus. Okay, it's literally just 1 plus whatever F1 is returning. So if I stop this, I can edit the code a little bit, because if this makes it look more clear, we can certainly do it this way. Okay, my keyboard is going a little too fast. There we go. All right. And then the PTR plus 1 is advancing to the next location. That is correct. So this program, okay, this F1 subroutine really should not involve any concept that CISP360 has not covered. I mean, really. Pointers, dereferencing, calling a subroutine, ternary operator, those are all concepts that should have been covered in CISP360. It's just that, we kind of use it in a funny way in this class. I'm not sure what Darvish is referring to using char since it's 1 byte. it has to do with, when we make a string is always an array of chars, and that's pretty much why we have a pointer to a char, because that's what each element is in a string. And then Omar is typing. This will not count the null terminator, because when the null terminator is encountered, when asterisk ptr is false, it returns a 0, which basically means if you try to pass it an empty string, it returns 0, which is the proper behavior, because that's also exactly what string length is going to do. So, in other words, if you make this an empty string, it would just return 0, which is proper because an empty string has a length of 0 despite using up 1 byte to store the null terminator, because the null terminator is not really exactly a part of the content of the string, even though it takes up 1 byte. So there's a slight difference between those concepts. And I think someone is trying to get in again. Alright, so let me see if I can get to that person this time. Alright, so okay, there we go. I got it this time. Alright. Alright. So let me go back to Discord, because I just switched over to the Meet window. Now I'm back on Discord. Yes, Jonathan, that is correct. So any scalar that has 0 as a value is considered false. So it can be a null pointer, can be integer 0, can be the null character, can be 0 as a double precision floating point value. All of those are considered false in the context of whether something is true or not. So in the context, like inside the condition of a conditional statement, or the condition of a loop, or the condition of a ternary operator. So when it needs to be interpreted as a Boolean thing, all of the scalar values with a 0, they're all considered false, and anything that is not 0 is considered true. So that's the thing about C and C++. There are a lot of type coercion going on that the compiler doesn't let us know. All right, Jonathan is typing. I'm gonna. Oh, okay, there we go. Oh, okay. Alrighty. And then Alexander is typing something. Omar is still typing something. No. So 0 as a character has an ASCII code of 30 in hexadecimal. So if you look up the ASCII table, the digit 0 is represented by the bit pattern of 00110000. So that particular bit pattern is representing the character 0. The null character has, it has no specific meaning other than, it is the null character. Okay. Yes. So the bit pattern of null is 00000000 as an 8-bit pattern. That is correct. So I'm addressing Marco's question in the text channel, because we have to differentiate between, are we talking about the code 0000, or are we talking about what character the code is representing? So there are two different kinds of zeros. All right, so if there are no questions about the C code, now it is time to translate that into assembly code. So strictly speaking, there's no need to really understand the C code or how it gets the job done, only that it gets the job done, to translate that into assembly code. But in reality, if we don't understand how the C code gets the job done, then it becomes really difficult to debug the assembly code, because we don't know what to expect from the assembly code. So there's a technical version, which means, yes, if you can do a blind translation from the C code into assembly code like a compiler, and that might work. But since we are not compilers, sometimes we make mistakes. It is not possible to debug the assembly language version of a C program without understanding how the C code works. So I just want to make that distinction. And now we're ready to write the code in assembly. Okay, so I'm just gonna locate one of my CLIs. I want the one that has a good sized font. Okay, because otherwise you guys cannot see the program. Okay, I think this one works okay, even though there's a little bit on the right hand side that's cut off. I think it's still okay in this context. And then we'll get started. So I just want to remind people also, VI is not a very simple and easy editor to learn. So there's a lot of tricks, that is not intuitive. If you're running short on time, you're taking other classes and it's the end of the semester, you got a whole bunch of homework and projects to do, it is not a good time to get into VI. Okay, I'm just being honest here. On the other hand, if you have time, yeah, I mean, you can go ahead and try to, invest some time into VI, but, once you run out of time, just go back to Notepad so that you don't have to struggle with the commands in VI. It takes time for all of those commands to sink in, to get used to it. All right. So now we look into this program and we say, okay, let's call this f1.ttp-asm. And we deal with the usual stuff, which is starting with a no-op instruction, do an unconditional branch to the label main, because main is going to be here. Main is going to stop with a halt at some point. And then we have the subroutine. Subroutine is called f1, and f1 eventually has to return. So we'll just put in the return code here right away, because otherwise if I forget, then the f1 is going to fall through to the code in main, and that's not that would not be good. So we will do the ld bd increment d jmpb, and that's the usual sequence to return to the caller. I'm not saying that there's anyone, but if anyone is looking at, okay, let me turn on the line numbers. If anyone is looking at lines 5 to 7 and go like, I have no idea what these 3 lines are doing, what the purpose is for these 3 lines, or individually what each line is doing, it's time for some review. Okay, in that case, because at this point in this class, I am expecting people to look at line 3 to line 7, excuse me, line 5 to line 7, and understand what each line is doing, and also what collectively all 3 lines are doing at the same time in the context of a subroutine being called. Okay, so that's, I mean, obviously that's my expectation, and people can do whatever they want. Okay, but I can only say that it's essential to get all of those concepts behind us, and so that we have the foundation to learn something new. All right, so main is so let's deal with main first. So in main we have 2 local variables. So this is kind of the fun part too. It's like, how do we define a string in assembly language, right? So that's one thing that's kind of interesting. And then the second part is these are both local variables. So str is a local variable, and so is x. So I'm going to use the concept that that you will see in tonight's lab. Okay, so this way, things will be kind of more coherent, because I'm teaching the same stuff as in the lab that you'll be doing tonight. Okay, so we got a few statements here. So Victor is correct that if we define main all the way up here, then you don't need the JMPI to main, because we just have main right after the no op. And technically speaking, we don't even need the label main if you just put the implementation of the main function all the way just right after the no op. So technically, yes, okay, but I want to preserve the order of the definition as in the C code, and that's why I just do a JMPI to main like that. So that addresses that. Yeah, so to respond to Chris's comment of but then it wouldn't match the C code, it's not really that big of a deal in this case, because we are not talking about the actual implementation in the subroutine. We are simply talking about can we change the order of the definition of the functions, and that really is not a big deal. Okay, so having that said, let's look at main. So the first thing we want to look at main is like, well, it's got two local variables. How do we arrange those two? So typically, the local variable that is declared first is also allocated first. So str is allocated first, and then x is allocated second. That means str has an address that is higher than the address of x. But together, okay, they both have to be allocated on the stack, and the initialization of str, that's a different thing. So we'll deal with the initialization of str, separately. So we'll deal with the allocation first, and then we'll go back and go like, okay, but how do we initialize str to a literal string? How do we represent a literal string in assembly language? So we'll handle all of those things, separately. So this means, as far as the call frame of main is concerned, I have to use, quotes, in this case, because main is not really called by anyone, but it still has a frame. This frame doesn't have a return address. It doesn't have any parameter, but it does have local variables. So from that perspective, main still has a call frame. So for that call frame, we have x being the last thing that we allocate. So it will be the closest. It will be right at where the stack pointer points to once we finish the allocation of the local variables. So x has an offset of 0 from where d is pointing to, and then the next one is going to be str. So str is x1 plus, because the size of x is exactly just 1 byte. So the offset to get to where str is from where the stack pointer points to is just 1 past where x starts. And then what I'll do here is I'm going to say main local var size. I know this is a long label name, but this is basically a label that represents how many bytes should I allocate for the local variables of main. So that would just be str1 plus. Str is the starting point of the local variable that occupies the highest address. And then the 1 plus basically says, str has a size of 1 byte, and that's why we have to add that byte in order to find out how many bytes of local variables main is going to need. Okay, so at this point, these are line 11 to line 13. These are all assembler constructs. They are not available at runtime. So I haven't really done a single thing with the register D at this point. Okay, absolutely none. Okay, because line 1 is no op, doesn't do a single thing. Line 2 is a JMPI, it doesn't do anything to register D. Lines 11 to 13, they are defining labels, okay, which means they are also not doing a single thing with register D. So the first thing, technically speaking, we should do with register D is to initialize it so that we have the stack pointer pointing to just 1 byte past the end of the entire address space. This is one way to do it, but sometimes you will see me doing it this way, which gets the same thing done, okay? Because if you subtract the register D from register D, and then store the result back into register D, what are you really doing? You're turning register D to 0. Yes, it does have a side effect of changing the flags, but nobody's paying attention to the flags right now, so it is okay, to do that. So I'm going to use this approach. I'm just looking at the text channel. Okay. All right. So the next thing we need to do is to allocate for the local variables. So now we have a LDI. Okay. LDI And you can use any register other than D, which is A, B, or C, with main underscore local var size. And then we do a subtraction. We are now subtracting A from D. So this will allocate local variables. Okay. I mean, at this point, those offsets become effective. So at this point, the label X is truly representing the offset in number of bytes of where I can find local variable X relative to where the stack pointer is pointing to. So at this point, they're good to go. But before we do anything else, I'm gonna do something. Okay, that's not. I'm gonna copy and paste 2 lines here, and I'm gonna do this because this one is just deallocating the local variables. Now this is really important because it is a subroutine's job to allocate space on the stack for its own local variables. But it is also the subroutine's job to deallocate that space before we get to the return portion of a subroutine. Because otherwise, the location of where we expect to find the return address would be wrong. So that's why it is important to, when we allocate, I just automatically write the code to deallocate and then just go back and fill in whatever code is supposed to go in between. Because this way I won't forget to close or forget to match the beginning code. So if I allocate, I'm going to have the deallocate code written right away so I don't forget. Alright, so now what do we do? Well, the first thing we need to do is to initialize str with that string here. Okay, so the question is, how do we do this? There are several ways to do this. Okay, there's a straightforward way to do it, and I think I'm just going to go for the straightforward way here. So the straightforward way to do this is to declare another label that marks the beginning of the string. So we'll just, I'm just going to use underscore as the first character. This way. Oh, okay, yeah, I'm going to use underscore to start the label definition just to make sure that we understand this is a quote-unquote internal label, because it only needs to be known by main. We'll just call this, str and then the colon. So this time I don't have an expression, right after str. You can, I mean, whatever name you want to use is fine as long as it does not collide with the other str. They have to be different. So this is just marking the beginning, and then we have the bytes, okay? Because each byte is defining the content of one single location in RAM. So there's no easy way to do this. I'm sorry. I just did not, make a language feature to define the string. So we have to define the string using. It has to be character by character. There's no easy way to do it. So what is the ASCII code of lowercase a? I cannot remember, but I can remember. Okay, 64 in base 10 is the starting ASCII for uppercase A. And if you add 32 to it, it becomes the starting point of lowercase a. But, since everything has to be specified in a postfix notation, it is 6432 plus. And then the next line, okay, next line. Oh, so the next line says, if we know where lowercase a is, b is 1 after that. So we just say this is 1 plus. And then 2. Yeah, I wish I had the macro capability in this assembler, but I was too lazy to write that, so that's why it does not have it. Alright, and then the last one is the Null Terminator, so it's just a 0 here. So this is how we define a literal string in TTP ASM. Kind of a pain, Oh, lowercase a is 97. Darn it. Okay. Then what is 96? Okay, I am curious now. So show me the man page of ASCII. Oh, doesn't backtick. Okay. Okay, that's fine. All right. So now we have. Thank you. And I'm just looking at this at the table now. I mean, I trust Chris. Okay, 97 it is. Oh, okay. So now we have A, B, C, D, E, F, and a null terminator. So the initialization of str is now just LDI. Whether you compute the right hand side first or the left hand side first really doesn't matter. Okay, I just in this case I'm just going to compute the left hand side first. Okay, the address of where we need to store the string. So that would just be LDIA str add AD. So now register A has the address of the local variable str, and then I load underscore str into register B, do a stab. So now we have just initialized str to point to the literal string down here. All right. So Chris is correct, because we are using postfix notation. You specify things first, and then you specify what you want to do with those things. And then Rachel said, he explains PostScript. Okay, so that is correct. There we go. The manual, by the way, the assembler manual also specifies, the syntax of the expressions being postfix. So it's good to read that manual too. All right, so now we have str initialized, and finally we can now get to the function call. Now x is not initialized, so we don't have to deal with that. So now we just go straight to line 22. First thing we need to do is to push the address of str on, not the address, the content. Okay, we have to push str on the stack. All right, so let's go ahead and do that. I mean, technically, you guys already know that we don't have to recompute everything, but I'm just gonna do it, so that we get some additional exposure. So at this point, register A has the address of str, but line 22 doesn't say passing ampersand str. It says we want to pass str, so we are not done yet. We need an LDAA so that we get to the value of str. Okay, and we want to push that on the stack. To push anything on the stack, you have to decrement the stack pointer first, and then store to what the stack pointer is pointing to. So this will push str on the stack. Then it is time to actually call the function f1. So at this point, we have the usual sequence, which is LDIA.6+, decrement the stack pointer, store to where the stack pointer points to, register A, which has the return address, JMPI to the entry point of the subroutine, which is F1. And at this point, whatever I specify on line 32 is going to be where the code will continue to execute after this particular invocation of F1 is done. So the first thing we need to do is to increment D, because we have to deallocate str as an argument from the stack, because it doesn't need to be on the stack anymore. And furthermore, it's going to offset the stack pointer, so it will change how I would find x if I don't deallocate it first. So also at this point, register A has the return value of calling F1. So I better not trash the value of register A until I make use of it. On the left hand side of the assignment on line 22, we have x. So now we have to compute the address of x. So we have to do LDI AX add AD. So now register A has the address of X, and this time we don't need another LD because we want to store to that location. So st will overwrite whatever A is pointing to, which in this case is my local variable X. And oh, I just said one thing and did another thing because I just trashed register A, didn't I? So I cannot do that, because register A needs to be kept. It has the return value of F1. So that's why I have to switch everything from register A to register B, because register A has a specific meaning at this point. It has to be preserved. And we got a question of what does add AD mean? I don't want to sound mean, and if it is interpreted as mean, I can't help it. But it should be understood by now. Now, the first thing we can do is to look at the opcode table, find out what the add instruction does. And then the second thing I think all of you should have done already is to understand how we come up with the opcode of add AD or add BD or whatever. And then the third thing we need to do is to understand the microcode of that opcode in the ROM of TTP, and understand what kind of pathway is being established between the components of the processor, and why and how, I should say, and how the operation is performed using the various components that are active for that particular one microcode slice. So if this sounds mean, I cannot help it. It was not my intention to be mean, not to answer the question directly. But I do think that it is really important that you guys know where to find that answer by yourself. And if anyone has the question in their head and go like, then why do we need you? Why do we need a teacher if we have to figure out everything? I mean, I can answer that question later, okay? I'm not going to use class time to answer that particular question. Okay, so that should conclude everything because we have the deallocation of the local variable right after this. And now we can focus on the subroutine F1 itself. The first thing we need to do is to figure out the call frame of F1. What should the stack look like when everything is allocated? Okay, so that's the most important part. So with F1, it is fairly easy because we have the parameter PTR on the stack, and then we have the return address also on the stack as well. PTR is going to be the one that has the higher address because it's pushed first by the caller, and then return address is the one that has a lower address because it is pushed second by the caller. And that's it. We don't have any local variables in this case. Now, for those of you who say, but we want to make the code really, really flexible, just in case we make F1 complicated later, and we want to be able to handle local variables, you can do something like this if you want to. You can say F1 underscore local var size, and just make it 0 because we don't really have any local variables. But once we have this, you can still do the usual thing, which is LDIA with F1 underscore local var size, subtract the stack pointer, subtract A from the stack pointer, and then later on, we do the opposite to deallocate, local variables if there are any. Okay, so we can still do something like this. Okay, you look at this code and go like, but tech, F1 underscore local var size is just 0. We are doing absolutely nothing. With these 4 lines of code, the 4 lines being lines 8, 9, and then 13 and 14 at this point, the answer is yes, we are absolutely doing nothing, but we are leaving behind a structure of code that will work very easily in case we do want to decide later on to have local variables. Then we don't have to go back and go like, okay, where do we do the allocation and where do we do the deallocation? We got that code already. We got the framework already. We just have to, recalculate or re-express F1 underscore local var size, and everything is good to go. So there's that plus, okay, by putting these sort of useless code in this case. So I'm just going to leave it here because it doesn't hurt anything. Okay, I'm getting back to the text channel. Okay. All right, so moving back to this code. So now we have the frame all set up, okay? Because register D, the stack pointer, is pointing to the base of the entire stack frame on line 11. So now we can start to write some code. The first thing we need to do is to check what PTR is pointing to. Okay, so we have LDIA. Okay, wait, PTR is not even defined yet, so we have to do that first. So we have to look at the call frame. And in this case, because we don't have any local variables, we can still define PTR, which is our only parameter, to be f1 underscore local var size 1 plus. Okay, because it is 0. And the reason why we don't want PTR to be we don't want the label PTR to be 0 is because there's something that taking that spot already. PTR is 1 byte after, okay, higher on the stack compared to whatever is taking the location of where the stack pointer is pointing to. So now and if you're wondering what is taking up that space, I'm going to let you think about that a little bit because I actually talked about it, and it is on line 5. Line 5 is already showing you what is supposed to be on the stack at this point. All right, so on line 12, we just say LDIA with PTR, add AD. So now we have the address of PTR in register A. So that is just ampersand PTR. So we have a LDAA. Let me see. Yeah, that'll work. So if I were to comment, okay, and I do encourage you guys to comment as well, when you're writing your code. So right now, register A has the address of PTR. By dereferencing it once, register A now has the value of PTR as a parameter. But we want to use whatever it points to, to check whether we should go to the then case or the else case. So typically, I would just do another LDAA, but I'm going to do LDBA. Okay, so the register B is whatever PTR points to, and then register A is still PTR. That's because I was looking ahead a little bit and I realized, hey, we need that back later on. We might need it back, okay? So since I do have a few registers to play with, hey, why not use up another register so that we don't have to recompute the value of PTR later on. So that's why I use another register, register B, to store whatever PTR is pointing to. So now we need to determine whether it is 0 or not, right? So technically speaking, it is a comparison to 0, but from the absolute value lab, we know that there's a shortcut to do this, because if all we need to know is whether it is 0 or not, or if all we need to know is whether it's negative or not, we can use AND, okay? Because that will get it through the ALU, setting all the flags, and we just need to look at the Z flag to see whether it is 0, or to look at the S flag to see whether it is negative. So that's the trick that we're going to do here, which is AND BB in this case. And then we have a JZI, to basically say if the Z flag is set, we will go to a particular label. So that label is going to be F1. I'm just going to call F1 else. And I'm going to define F1 underscore else right away so that I don't forget. And typically, when I do a conditional branch, I would write down what it means to continue and not to do the branch. So in this case, this is the then branch recursive call here. And then the else branch is going to be corresponding to return 0. Okay, and because this is a if then else kind of structure, by the time I get to the end of the then branch, I really need to get around the else branch. So I'm going to do a conditional branch around it, unconditional branch. I'm going to do an unconditional branch around the else case. So this would be F1 and if, and that's going to be F1 and if is here because it has to occur right after the else statement. All right. Okay, so I'm just checking the text channel, make sure I'm not missing anything important. All right, so we can always do the return 0. That's super duper easy, right? Just LDI A with 0. Okay, that will get the job done. Or if you say, but Tech, you just showed us a tricky way to zero the content of a register. It's called sub AA. Yeah, that works too. Okay, so it's up to you. So now we get back here and handle the slightly more complicated case of calling F1 again. First question, okay? First question in our head is, do we have to do this, kind of differently, compared to calling F1 from somewhere else because it's calling itself? The answer is no, okay? That really is the trick of understanding the mechanism of recursive call. It is not different from any other function call. It really is not, okay? Whatever you do with a regular function call, you do it here because it really is a regular function call. Just because a function is calling itself doesn't change the mechanism of calling, of invoking a subroutine. So that really is the trick of understanding the implementation of recursive call. It is not special in any way, okay? All right. That is correct. Jonathan is correct that sub AA uses one fewer byte and is also a faster instruction because it doesn't need to read an extra location in RAM. But we are not going to shave, execution cycles here. So, either way is fine. Okay, whichever one you want to use, LDA0 or sub AA, both will be considered equally correct. All right, so getting back to here. So we have to compute PTR plus 1 first. So fortunately, I had the foresight to know that we still need PTR, or the value of PTR. And on line 14, we had it computed in register A, and it's still in register A at this point. So I can just say, register A still has PTR. Make a little point here, making sure that I remind myself that register A still has it. So what we need to do is just to add 1 to register A before we push it on the stack. So we have increment A, to implement PTR plus 1, and then we push it on the stack. Decrement D, ST, D, A. So now we have just pushed PTR plus 1 on the stack, and it is time to call F1. But wait, Tech, didn't you have the code to call F1 from main? Can't we just kind of copy and paste that code here? Yeah, sure, why not? So we go to main and we locate the code to call F1, and that would be from line 54 to line 58. Okay, so collectively it's from line 54 to line 58. So we say 54 to 58 Y. This is the command in VI to copy. And by the way, Y stands for yank. Don't ask me. That's just the way it is. And then we do a paste, okay, lowercase p for paste. So now we have copy and paste. Cool. So now we have the return value sitting in register A. The extra byte used by the argument PTR plus 1 is gone because of the increment D. And of course, I really should change the comment so that we can make sure that we are matching the description of what we are implementing. Okay, so now we have register A having the return value of F1, and we're supposed to add 1 to that to be my own return value. So now we just say increment A. So now A is 1 plus F1 blah blah blah. Okay, and we're done. We are done with the then branch. This is specifying the else branch. And the else branch does not need to jump over anything because it naturally falls through to the end if. So now we get to the end if, and we go like, but Tech, we have a problem here. because we are trashing register A, which is now important because it's already specifying the return value. Yep, I forgot about that. So let's use some other register, like register B. There we go. Okay, I'm looking at the text channel, and how much RAM? Okay, with how much RAM we have, that could really help with larger programs. Oh, okay, so that means we are minimizing the instruction count because we only got 256 bytes to play with. Yep, very good. But I'm pretty sure this program is short enough that it can fit all in 256 bytes, even with a little wasteful stuff that I did in this program. Cool. Okay, so I think the program is done. Okay. The fundamental limit to recursion has to do with how much stack you have. That's about it. So if I have enough stack space, there's no inherent limitation of how deep I can go in recursion. So it all has to do with how much stack space is available. All right, cool. So let me look at the time. We got about 8 minutes left. So it's time to do the worst part of doing homework assignments. And if you think doing this kind of homework assignment is bad, wait until you become a software engineer or developer where you have to debug the code that somebody wrote 30 years ago, and you can't even call that person to ask anything anymore because that person probably has passed away already. Yep, that's the kind of fun stuff that you get to do when you graduate and you become a software engineer or a developer. I call that fun. Okay, your detective work is fun. So now the question is, how do I test this program, right? Because if this is what I'm supposed to do, okay, everything seems to look okay. I caught a few bugs myself, like trashing register A when it already has the return value. So what do I do? So what I need to do now is to anticipate what the program is supposed to do so that when I look at the trace, I get to see, okay, I'm expecting it to do this. Is it doing it? I'm expecting it to do this. Is it doing it? And the moment it is doing something I'm not expecting, then I go like, wait, hold on a second here. Okay, this is a deviation from what I'm expecting. Did I, okay, so there's a discrepancy. Okay, is the program wrong, or was my expectation wrong? When I try to run the program in my head. So we have to do all of that stuff before we even try to assemble the program and and get it to work and collect the trace. All right, so we got some traffic here. Documentation. Well, everything in this class is quote-unquote documented because it's open source. That's the beauty of open source. It's like, yeah, you get the source code, play with the source code, read the source code, and understand everything. Yep. All right, so let's go ahead and look at the program here and figure out how the stack is going to be used. Okay, so that is really, really the important part of assignments like this, is to figure out the behavior of this program. Now this is also a single recursion point kind of thing, which is easier to debug because when you have a double recursion thing, things get a lot more messy because it's not just going this way all the way and then going back the other way all the way, because it's going like zigzag, 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 and that makes it kind of difficult to debug. But this one is not. This one is not like that. So what we do is we look at location FF, we look at location FE, FD, FC, FB, FA. Okay, we'll just start with these. Okay, and they have there's no need for these columns to be that wide, so I'm gonna make them a little bit smaller, just so that we can fit more stuff on the screen. And obviously I don't have to magnify this to 180%, so we can shrink it a little bit. This way we can fit more stuff too. All right, so from the perspective of main, the first thing we did was to allocate for str. So location ff is used by local variable str of main, and then fe, which is the one right below that, is used by local variable x. So these two combined is quote unquote the call frame of main. So if I want to make it clear, I can just kind of merge these two cells and say these two bytes make up for the call frame of main, which only happens once because because main doesn't call itself. And then what we do is we look at location fd. What is the next thing that we put on the stack, right? Well, the next thing that we put on the stack was the argument to call f1. So even though it is the value of str, the role that location fd is playing is ptr, okay, because it is a parameter of f1. And then right below that is our return address. So I'm just going to abbreviate return address to RA. So these 2 bytes become the call frame of the first invocation of f1. All right. So by the time we get to the first invocation of f1, we look at the first byte that ptr is pointing to, and it is not a null because it is lowercase a. So we're going to call f1 again. But when we call f1 again, this fb is going to be ptr plus 1. So if you want to track the actual value of this ptr, this one is going to be str itself. Okay, wherever it is, that's something that the assembler can help us determine. But whatever we push to location fb, which is the second invocation of f1, this location, which is also serving the role of ptr as a parameter, is going to have the value of str plus 1. So that is the important part. This is also going to be the return address, but it's not a return address back to main anymore. It is the return address back to another invocation, an earlier invocation of f1. So that part is kind of needs to be, it kind of is important too. So this, if you want to make this more clear, you can say this is the return address to main, and this one is the return address to f1. Okay. So it does get a little bit complicated. Okay, so this is another call frame of f1. This is the second invocation of f1. So you can kind of imagine that we are going to use the stack a few times like this, right? So we're going to have f9, f8 kind of be the third frame, and then we have f7, f6 as another one. So at this point, I'm just counting. Okay, so this is another f1 call frame, and this is going to be another f1 call frame, and we have str, str plus 1, str plus 2, str plus 3, and we need 4, 5, 6. So we need 3 more of these. Okay, I'm just counting because I can do a copy and paste of columns. There we go. So that makes it a little bit faster, when I want to simulate, what the stack is supposed to be doing. Now, obviously, I have to backfill all of these things here. So this is ptr, as a parameter, but the value of this one is going to be str plus 2. And this is also going to be return address to f1. And then with this call frame, we have this is ptr2, this is str plus 3, and this is going to be str plus 4, str plus 5. This is going to be str plus 6. Okay, so by the time we get to the 7th invocation of f1, we finally encounter the null terminator. So at that point, we stop the recursion. We stop calling it f1 recursively, and then we start to return. So that means when we're looking at how RAM is going to be used, it is going to consume RAM space all the way down to location f6. and then it will back up. The stack pointer will go back up again, and we can also expect register A to get a value of 0 at this point, and then it goes back up to 1, 2, 3, 4, 5, 6, and then by the time it gets to main, it will be 6, and then we'll store the value of 6 into location FE. Alright, so I'm going to catch up with the text channel here. An invocation means a call. A single call is an invocation. Yes, so at time mark 650, yes, Sasha is correct. When we call F1, it is an invocation. Yes, so Omar is also correct that each call adds 1 frame, as long as it is called with before the other one returns. So we have 7 frames here because we have 1 frame for str, str plus 1, plus 2, plus 3, plus 4, plus 5, and this is plus 6. Because until we get to str plus 6, which is where the null terminator is, we cannot stop the recursion. It will keep going until this point. Okay, so now that we have this general picture of what the program is supposed to do, now we can get to the assembler and try to get it to work. So I know we are running out of time, but I think it is sort of important to finish this. Yes, I have a lot of IBM tabs because of my CISP310 class. But right now I'm trying to find my assembler. Okay, so go all the way back up. And also make sure you use the latest version of the assembler. I haven't really changed the assembler this semester, but I had an obsolete one earlier in the semester, so make sure you're not using that one. Okay, so we get rid of this, and then we go back to the command line interface. And the way I do this, okay, this is not going to work in Windows, but Windows has something similar. In Windows, you just kind of replace xclip blah 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 with clip. Okay, that will put the content of your VI buffer into the clipboard. Then you can paste into whatever you want. Okay, so now I go back to column A, and then just do a regular paste, and wait for the assembler to be done. And one thing that we might want to find out is where is str, or underscore str, I should say, because that's the starting point of the literal string. So the literal string is here, which is at location 42 in hexadecimal. Okay, so at location 42 is in hexadecimal. So if I go back to my spreadsheet, now I can say, okay, now we know what to expect here. This is 42 in hexadecimal, 43, 44, 45, 46, 47, and finally 48. Okay, so at location 48 we have the null terminator, and just to double check again, okay, this is our null terminator. This is the address in hexadecimal, so we got that part. So now we can go to the RAM file, and file, download as CSV. And you have to kind of configure your browser, not to save it automatically and create a new name, when the file already exists. So just Google to find out how to do that to your own browser. Okay, so we'll call this one f1.csv. Switch back to the command line interface and specify the long command. And I'm gonna cheat a little bit here, because I can just kind of copy and paste most of what I have from before and only change the CSV file that I'm loading into RAM. So in this case, it is f1.csv, and then the output goes to f1.tsv. Press the enter key. Hopefully I did not make any stupid mistake, because if I did and this becomes a infinite recursion, then it may not even come back because I might not even get to the halt instruction. So, so there is that problem. Okay, occasionally it's like that, but you can still type Control C to stop the process. Then you'll have a partial trace, and that should help you find out where the infinite loop is. So it's still not hopeless. It is still usable, even if you have an endless loop and it doesn't exit by itself. So now we get to the trace analyzer, and then we use file import. And we just upload f1.tsv, which we just created a little bit earlier. So f1.tsv. Replace current sheet specified tab as a separator, and then turn off automatic conversion. Okay. And just wait for the progress bar to finish. Then we get to summary. This is kind of long, longer than the other programs that we have seen. The last line is row 875. So we get to analysis. And let me see if there's a quick way to get to a particular row, like go to. None that I can find. Pretty sure there's a shortcut key to do that sort of thing. I cannot imagine that we don't have a shortcut key just to get to a row. But, not too bad. We can just kind of scroll through to, what again? 875. There we go. Alright, so this is 875, and the last instruction that we execute is at location 41. So we want to double check, make sure this is our halt instruction. Okay, so we go back to the assemble tab, and then we go to the halt instruction, and it is indeed at location 41 in hexadecimal. So that's good. Okay, so far, at least the program got to the halt instruction to stop. And we also confirm that by the time we get to the halt instruction, the stack pointer is back to 0, 0, which is also good. That means we didn't use any. The stack is now balanced. Okay, so these are very good signs that the program probably worked the way it's supposed to. And then we look at location FE. It eventually got a value of 6. So we compare this with the earlier analysis, and we say that location FE is indeed where X is supposed to be, and we know X is supposed to get 6, a value of 6. So that is also a good confirmation. Now, it doesn't really mean the rest of the program is 100% correct. Okay, this is but it does mean that there's a very high likelihood that everything is working, because if something is not working, either the wrong value will be returned, or the stack is not back to 0, 0, or something is going to happen. Okay, something nasty is going to happen. But as far as I can see, this is all kind of doing okay. So this is the sort of thing that I want you to do with your swap subroutine. Is when you before you try to run the code, you should know what it is going to do. So you might be thinking, oh man, this is, do you mean that I have to kind of predict what my code is supposed to do, with 800 something rows in a trace? Your program is not going to have this many lines of trace, because I specifically implemented something that has a loop nature in it. That's basically what recursion is doing, is basically a form of loop. Your code does not have a loop. Okay, so it's going to be a whole lot shorter compared to this. And it doesn't have recursion either, so that means you only have one level of function call, main calls swap. That's it, right? So the analysis of what you should be seeing on the stack is nothing like this. Okay, you probably would use up like maybe column D, maybe column E, maybe column F. That's it, because you only got main and also swap. Swap has its own local variable. Okay, so it does use up 1 byte, because of that. So main has 2 bytes because you have x and y, and then swap has the parameter, two parameters, the return address and also the local variable. So, in the case of the swap subroutine, you will be using columns A to F. So the analysis is not going to be nearly as ugly as what we see here. So, but I'm giving you this trace today because, I just want you to get another view of how to implement C code in TTP-ASM. So I think I'm done here. So now we can go back to the activity that I want you to do today. Because somebody asked me, so does that mean we don't have a lab tonight? No, we have a lab tonight. So it's called call frame. Okay, hopefully it will help reinforce some of the concepts that I have just talked about in tonight's lab. And there's a key, access key to this one. Okay. So this one does allow multiple attempts. Okay, so for those people who want to just try out every single possible choice of a multiple choice, there are some questions with multiple choice, but some have values. Okay, so it doesn't work all the way, all the time. The access code is framed. Okay, so I'm gonna put it in the text chat channel, framed, and I will pin it. There we go. All right, so there it is. Okay, and the due date or when it's due is 9:50 p.m., the usual end time of our lab session. There we go. Oh, okay, that's a good question. I don't think lowest is an option. So we have highest, latest, and average. There's no lowest as an option. Oh yeah, I can upload everything with F1. Okay, so I'm just going to I didn't make any changes, but I'm saving it anyway. So you guys should be able to see the lab at this point and use framed to access the lab while I upload F1 blah into onto the Discord channel. So I have F1, all the F1 stuff except for F1.c, which I don't think is super duper important. Okay, so I just go like zip dash f1.zip, f1.ttpsm, f1.csv, f1.tsv, and then put it up here. Cannot find it. That is odd. Okay. All right, I'll do it one more time. There we go. All right, and I'm gonna pin that one. And thank you, Jackie, for the screenshot. I'm gonna pin that one too. All right, so I'm gonna sign off, and and I'll be back in about 10 minutes. Okay, so you guys go ahead and get started with the lab.